Hey everybody, today we're going to be going over the real-time implementations of the timescale modification algorithms that we learned about in class. So the motivation for this project was to take the TSM methods that we learned about in class and implement it offline and implement them in real time. And the point of this was to further our understanding of the concepts at hand and also improve our signal processing capabilities.
So we first start with the overlap add algorithm or the OLA. And this algorithm is very intuitive. Its fundamental approach basically involves with segmenting the input audio signal into overlapping windows referred to the analysis frames, as you can see here in the diagram. The window is characterized with its length L and its analysis hop size H of A, where the stretching actually happens when we have a new hop size called the synthesis hop size or H of S. You can see that we have the relationship between H of A and H of S here, where alpha, our time stretch factor, determines how short or long your stretch would be. And the reconstruction of the signal happens when we have our synthesis frames. And what makes synthesis frames and analysis frames different is that we actually apply a window function that allows continuity within the signal. And yeah, so now we have our synthesis frame, overlap add, hence the name, then we'll have our stretch signal. It's important to note that the signal or this algorithm is actually best used for percussive signals.
So now we're going to move on to the phase vocoder and then some of the logic that works behind it. So essentially, the main idea of the phase vocoder is to take windows of the original signal and then perform the STFT on each one of those windows to develop an STFT matrix. And from there, we can essentially modify the phases that are present within each frame of the STFT matrix. And essentially, we do that to account for any changes in phase and to ensure that there is phase continuity between each frame. And to get to our synthesis frames, we essentially perform an inverse FFT on each individual frame of the modified STFT matrix, since the STFT is not necessarily invertible. And once we have our collection of synthesis frames, then we can perform overlap add so that we can successfully reconstruct the signal. And we cannot forget to window each individual synthesis frame, similar to how we do it in OLA. And in this case, for our implementation, we had a window length of 2048 samples, and we had a synthesis hop size that was a fourth of that, so 512 samples. And yeah. So moving on to why exactly we need to modify the phase, as we can see in the center, if we don't modify the phase, the signal of two adjacent frames can actually destructively interfere with one another, which will create many artifacts and phase issues. But if we do successfully modify the phase and account for any phase changes, then we can see on the far right of the diagram that adding two different frames will actually constructively interfere, which will produce a clean time stretch signal. It's important to note that the phase vocoder works best with harmonic signals since it maintains phase continuity across different frames as opposed to different frequency bands.
So now we move on with the hybrid method where we have two things in our toolbox now, the OLA and the phase vocoder. The main idea is that we want to separate the percussive signals or parts and the harmonic parts of the input signal, then having those two things go through their corresponding algorithms, then having the output signals added together to create our full stretch signal. And how we do this is basically doing a median filter on the magnitude spectrogram, where the median filter actually handles outliers really well. Even if there's a sudden spike or an unusual value, the median still reflects the surrounding values and doesn't get thrown off. So to enhance harmonic content, we expect a horizontal filter a long time because harmonic stays consistent across time. As you can see here in the harmonic separation, the shapes are horizontal. And when we see the percussive content, we actually see the opposite, where things are vertical, and hence we want to have a vertical filter. Since now we have these two shapes in mind and two filter spectrograms, we can create binary masks to hide ones and zeros to isolate harmonic and percussive parts. Applying these maths to the original STFD gives us two separate signals, one harmonic and one percussive.
So now we're going to dive a little bit deeper into the real-time processing aspect of our implementation. So the way we reconstruct our signal is through the use of an audio buffer that is supposed to imitate, essentially overlap add. So basically we have an audio buffer that stores data of the current frame. And in order to simulate a shift and add, we're going to push samples out of the buffer that are specified by the synthesis hop size. So say if your synthesis hop size was 256 samples, we would push out the first 256 samples out of the buffer and to the speaker. And once we push out those samples, we are going to add the next frame to the remaining audio data that is left in the buffer from the previous frame. And we're going to repeat this for the entire signal, basically ensuring that our COLA requirement is always satisfied. And this is important because it allows us to essentially perform the TSM frame by frame, which as a result allows us to treat alpha as a dynamic variable because now we can apply it to a single analysis frame without expecting the next frames to have the same alpha.
So now in our real-time time stretching algorithm, we can process the audio as it arrives. But we can separate this work into two parts, pre-computation and live processing. In our pre-computation, we separate the input signal from its harmonic and its percussive components using the HPS algorithm mentioned before. And this lets us choose the best stretching method for each type, which is the PV, phase vocoder, or the OLA. So in the real-time stage, we can actually see that the PV analysis window length is bigger than the OLA. And because of this, we want to see how many OLA frames correspond to one. And through this, we can have these two methods go into parallel with each other. And the first part is basically doing the phase vocoder, getting all the information, putting it into the buffer. And then the second part is the OLA, where we see here in the example, it has 4 corresponding OLA frames. And then we calculate the OLA synthesis windows, add that to the buffer along with the PV information, send that out as a full signal, and then we can have our time stretch signal into our speakers. And now we have a demo.